Hello students. So in this video, I'm going to talk about intermolecular forces, and you guys have already learned about shapes of molecules, polarity, net, overall dipole moment. So we're going to bring that all together, talk about how molecules interact with each other, and then connect that with some physical properties of liquids. So this is our intermolecular forces section, and sometimes you hear that called van der Waals forces. Basically, it's just forces between molecules. So be very careful. This is not the actual bond like a covalent bond or an ionic bond. Those are very strong. Those are why matter exists. Intermolecular forces are the forces between those molecules. And the key underlying principle behind that is the fact that opposite charges attract each other. So plus attracts minus. I'm going to talk about four different ones. The first one isn't necessarily between molecules, but it's between an ion and a molecule. It's called ion dipole. Then the rest are between molecules: hydrogen bond force, dipole-dipole, and London dispersion forces. Ion dipole, you guys are familiar with because we've dissolved ionic compounds. It's between an ion and a polar molecule. A cation will interact with the minus end, for example, of water, the oxygen end of water. An anion here will interact with the plus end of water, the H's on water. A hydrogen bond force is a very strong force between molecules. It's not as strong as a covalent bond, but it's still pretty strong. And it only exists when you have an NH, OH, or FH in the molecule. So here's water. It has a lone pair. You guys know this is a part negative end. It's going to interact with the part positive end of an H. And this H does need to be attached to an NO or F. The reason why this is so strong, and look at how I'm showing it, it's not a real bond with a line, it's just dot, 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 dot. That's a hydrogen bond. The reason why it's so strong is because NO and F are some of the most electronegative elements, so it'll create a strong dipole, and the hydrogen and these atoms are quite small to get close to each other. You can also show this for nitrogen and hydrogen as well. So notice, oxygen special because it has two lone pairs, so it can actually form two hydrogen bonds. Also, you can have a vast network throughout where the H here is interacting with another N of another ammonia molecule and just have a vast network. This is actually really cool because it explains the pairing, the base pairing in DNA. So I know you've learned that A matches with T and cytosine matches with guanine, but why? Here are the structures. It all has to do with hydrogen bonding. Here's thymine with the O and an NH. Here's adenine with the N and an NH. These were perfectly lined up to have this hydrogen bonding. And you notice how, do you remember how like DNA can unravel its base pairing connectivity and then come back together? It's because these aren't real covalent bonds. These are just forces, slightly weak. They're weaker than covalent bonds, so they can be broken a little bit more readily. Cytosine and guanine also match up, and they actually have 3 hydrogen bond points. Okay, the next is dipole-dipole. The easiest way to remember this is dipole. If you have a dipole, you have a polar molecule. So dipole-dipole is between antipolar molecules. SH2 is an example. And notice, H and S, if you look on the table of electronegativity, their electronegativities are negligible. The difference is negligible. So that bond actually isn't polar. The only thing making this polar is that it's asymmetric with these 2 lone pairs. Either way, you have a part negative and a part positive end. And the whole dipole-dipole network will just be plus attracted to minus, any which way, plus attracted to minus, up, down. Maybe it's a little more disorganized than this. The one thing I'll tell you though is the more polar the molecule, the greater the strength of the intermolecular forces. So if you have a greater dipole moment, and you know different molecules can have a greater dipole moment, then the intermolecular forces increase. This becomes important later if you want to disrupt this network. London dispersion is the only force present in nonpolar molecules. It is present in all molecules though. So when molecules that are nonpolar are by themselves, nothing's happening. But if they can shift their electron cloud, so for example, say something that's polar gets near it, or it's influenced in some way, the electron cloud in here can shift to one side and create an instantaneous momentary dipole that can propagate and spread throughout. So this is a very weak force, but it can still be strong if you have a lot of them. For example, a Velcro piece has just a little hook by itself. A little teeny hook in Velcro doesn't stick much, but if you have a big patch of Velcro, that can hang paintings on the wall. Polarizability is a term you need to know. It's the ability to shift these electrons or the whole electron cloud in a molecule. This allows for us to create the London dispersion forces, and it enhances the dipole for a polar molecule. Larger molecules can do this better. So I2 has more electrons than F2, so it's more polarizable, and it'll have stronger London dispersion forces. The intermolecular forces will be stronger. So those intermolecular forces would be harder to break apart. Okay, let's practice here. What intermolecular forces do you expect in each of the following? So pause this and answer these questions. And then I'm going to go over it. Okay, so for pure ammonia, the first thing you should think about is, if you're not sure, is basically draw the molecule. This is polar just because of its shape. It's trigonal pyramidal, it has a lone pair on one end. But it's not just going to have dipole. Because it has an NH in it, it'll also have hydrogen bonding. And then all of them have London dispersion forces. So all three of those. For methane, when you draw this, it's a perfect tetrahedron, but C's and H's don't have a dipole anyway, so this is nonpolar. So the only possible force it could have is the London dispersion. For PCl3, phosphorus is in the same group as nitrogen, so it'll also be trigonal pyramidal. But it doesn't have the NH, it doesn't have any hydrogen bonding. So the only thing present here, not the only thing, but one of the things present is the dipole, and it'll also have the London dispersion like everything else. Okay, so if this is hard for you, take your time. Draw the structure, figure out the shape and overall net polarity. Then make your decision. For molecules that are polar and have dipole, just double check. Is there an NH, OH, or FH? And in that case, it would also have hydrogen bonding. One of the things we need to do is connect this whole polarity and intermolecular forces with physical states, solids, liquids, and gases. The only reason why solids and liquids exist is because of the forces between molecules. So the stronger it is, the harder it is to also break it apart into a liquid or even a gas, completely break it apart. And here, just going solid to liquid, you're just disrupting the intermolecular forces. This is going to require energy. Breaking it apart completely to gas will also require energy. This is related to melting and boiling point. So if I go from a solid to liquid, that's melting. I need to add energy to disrupt that intermolecular force. The stronger the force, the harder it is, the higher the melting point. This is related to boiling point as well. In this case, you're just going from liquid to gas. Stronger the intermolecular force, the harder it is to boil, the more energy it takes, so the higher the boiling point. This is showing increasing a dipole moment And as you increase the dipole moment, as we go left to right, the boiling point increases in yellow. So this does track with intermolecular forces. So I just want to show on this chart, I'm going to break it down. Each color here is a group on the periodic table. So this is group 4, carbon, silicon, germanium, and tin. All of these groups, as you go down the periodic table, the boiling point increases. Think about why that is. As you go down the periodic table, you have more electrons to work with, greater polarizability. So you're enhancing dipoles or you're having greater London forces. So all of these are going to track. Some are higher than others because look at this group. Red, group 6A, that's like water, and it's kin. Those will always be bent shapes. These will be trigonal pyramidal. So right there, you have an inherent polarity to these. So that's why overall those groups are higher than other groups. But why do we get this deviation here? Why are these off the chart? Look at these guys, water, HF, ammonia. You could pause it and think about it. Why are these off the chart? What sort of intermolecular force is present in those that's causing this to have such a high boiling point? So the answer, you may have come up with that, is because of hydrogen bonding. I told you hydrogen bonding is way stronger than dipole-dipole and of course London dispersion. So it makes the forces harder to break apart, harder to boil. As we go down the periodic table, because polarizability increases and consequently the dispersion forces, boiling point also increases. Molecular shape can make a difference. So I've got pentane here, 5 carbons and hydrogens attached to fulfill the octet. Here I have neopentane, same formula, but different connectivity. Look at the difference in boiling point. Can't just be explained by polarity because both are nonpolar. 36 degrees C versus 9. The reason is that this N-pentane, which stands for normal, just a straight chain, is more spread out. There are more contact points when it gets close to another molecule, instead of just this more dense structure that only has a smaller contact point area. So it's basically like having a larger strip of Velcro holding something together versus a small little piece of Velcro. The one that has more surface area is going to have the higher boiling point. So just to reiterate, hydrocarbons are nonpolar and only have dispersion forces. But as you increase those contact points, so here, these are all hydrocarbons, but greater and greater lengths, you get much higher boiling points, all the way past even water, over 100 degrees C. So head to head, dispersion forces are weaker than dipole-dipole or hydrogen bond forces. But if you have a really large surface area, they can sum up to be very, very strong. Here's an example of hydrogen bonding. And these have OHs. If you increase the number of OHs, you increase the boiling point. If you increase the number of NHs, you also increase the boiling point and melting points as well. Okay, that's where I want to end. We will talk next time a little bit more. And actually, we're actually going to go into gases. So that's our next section. All right, I will talk to you guys later. Bye.